In modern C# backend engineering, the async and await keywords built around the task API run everything. They manage network calls, databases, and concurrent operations. For the vast majority of applications, this system works exactly as intended. Developers write sequential code, and the runtime handles the asynchronous complexity automatically. But as throughput scales to millions of requests per second, treating a task as an opaque box hides significant costs. The abstraction begins to leak. At high scale, architects confront three distinct bottlenecks hidden behind the await keyword: phantom thread assumptions, heavy garbage collection heap pressure, and swallowed system exceptions. To write truly high-performance C#, we have to strip away the syntactic sugar and look at exactly what a task is doing at the bare metal. By understanding the underlying state machine, we can engineer systems that scale efficiently without collapsing under their own memory and error weight. Inside the .NET runtime, calculating the true cost of a task requires distinguishing between two entirely different types of asynchronous execution. The first is the delegate task. These are CPU-bound operations, heavy mathematical calculations, or data parsing routines. A delegate task locks a thread from the thread pool to a CPU core for the entire work duration. By contrast, a promise task handles I/O-bound operations. The thread hands a memory address to the network interface card, detaches immediately, and returns to the pool. The hardware takes over completely. The device driver handles the data transmission directly into memory via direct memory access, requiring zero CPU involvement. Once the requested data finally arrives, the hardware sends a brief electrical interrupt signal back to the CPU. This interrupt is intercepted by the operating system's I/O completion port. The completion port notifies the .NET runtime, which reaches into the thread pool and grabs a completely different thread to execute the rest of the method. Because the waiting period consumes exactly 0 threads, standard asynchronous I/O achieves massive concurrency. A system can maintain tens of thousands of active network requests using only a handful of actual threads. Explicitly creating or blocking threads is only necessary when navigating strict low-level operating system constraints, like requiring a specific processor affinity or COM apartment state. If an I/O task isn't bottlenecked by thread limits, its primary performance cost must exist elsewhere. That cost is memory allocation. .NET memory relies on two primary zones: the lightweight, fast-clearing stack and the persistent, garbage-collected heap. Here we see the memory layout. Because the standard task is a reference type, every instantiated task object must be allocated on the heap. Consider a hot path in a high-throughput API continuously calling memorystream.readAsync. When data is already buffered, returning a standard task forces heap allocations. In a tight loop, these allocations accumulate until the garbage collector freezes the application. The ValueTask struct solves this exact inefficiency by instantly resolving on the lightweight stack, completely bypassing the heap. Migrating from task to ValueTask on hot paths where synchronous returns are frequent eliminates this GC bottleneck, preserving throughput. While ValueTask prevents allocation for instant data, a truly asynchronous completion still forces a hidden task allocation under the hood to track the pending state. To eliminate this final allocation, .NET Core 2.1 expanded ValueTask to wrap a highly specialized interface called iValueTaskSource. This interface defines exactly 3 methods that govern state tracking for an asynchronous operation. GetStatus checks the pending state. OnCompleted attaches the continuation callback. GetResult fetches the final data. By implementing this interface, APIs like socket.receiveAsync can use advanced object caching to eliminate allocations entirely. In this diagram, the API maintains a single, highly reusable object. When a socket read begins, it borrows the object to track the state. Once the read finishes, the object goes back into the pool. The caller never receives the pooled object directly. They receive a lightweight ValueTask acting as a temporary pointer. The moment the caller awaits the result, data is extracted, and the underlying object is instantly wiped and recycled for the next operation. This continuous reuse achieves zero allocation asynchrony, that it imposes severe engineering constraints on the developer. First, you can never await a ValueTask multiple times. By the time you attempt the second await, that pulled object may have already been reassigned to track a completely different network call. Second, you cannot await it concurrently. The underlying object expects exactly one callback from one consumer. Violating this guarantees race conditions and catastrophic state corruption. To safely cache the result or await from multiple threads simultaneously, you must call .asTask to convert it into a standard heap-allocated object. Object pooling grants true zero allocation scalability, provided you strictly adhere to one-time linear consumption. These same state tracking rules dictate how we orchestrate multiple tasks running in parallel. Consider a scenario using task.whenAll to call 9 external web services simultaneously. 2 of those services fail, but the application logs record only one exception. Tasks are complex state machines designed to aggregate all operational faults into a hidden tree structure. This diagram illustrates that structure, known as an aggregate exception. When multiple parallel tasks fault, they compile their individual exceptions into a single tree. However, the await keyword applies deterministic unwrapping logic to task.whenAll. It intentionally surfaces only the first exception it finds, based strictly on the array order. Subsequent failures remain trapped inside the aggregate box, masking them from the outer catch block. This design choice prioritizes developer ergonomics, allowing standard try-catch blocks to function normally at the expense of complete system fault visibility. Retrieving every error requires bypassing the await keyword's default unwrapping behavior entirely. Instead of directly awaiting the whenAll call, you attach a manual continuation utilizing the only on faulted option. This explicit continuation provides the raw aggregate exception. You iterate directly over its inner exceptions collection to extract and log every distinct failure from the parallel run. Building resilient parallel systems requires manually traversing this fault tree, rather than trusting the primary execution context to report the full state. The unifying mental model is clear. A C# task is not a thread. It is a highly optimized state tracking promise. For standard web APIs and line-of-business applications, the default async and await syntax, along with standard task allocations, remains the correct engineering choice. These abstractions brilliantly trade minor memory penalties and deterministic exception masking for unparalleled developer ergonomics. But game engines, custom networking libraries, and high-throughput APIs represent a strict edge case where that abstraction degrades performance. In these environments, you maintain throughput by enforcing zero allocation asynchrony, leveraging stack-allocated ValueTask structs and I-ValueTask source object pooling. And you ensure system resilience by extracting the aggregate exception tree during parallel execution to maintain complete fault visibility. To engineer systems that process millions of concurrent operations, architects must stop treating tasks as black boxes and take direct control over the underlying state machines.